We talked about why we use RAG in the previous lesson. It helps solve AI hallucinations and provides tailored answers with your non-public data. But how exactly? The story starts from embeddings, which is the first step of the RAG pipeline.
What are embeddings?
Well, as you know, the input data of a Gen AI model comes in all sorts of formats: text, images, audio, video. These are called multimodal data. How to represent multimodal data numerically while preserving its meaning is the real challenge. Take text data as an example. Text representation techniques progressed dramatically in the past 2 decades, starting from basic vectorization, which refers to some intuitive ideas to encode the text to numbers. For example, one-hot encoding, where you first index the entire vocabulary, which can easily be tens of thousands. You then place a 1 to the position that corresponds to the word, and zeros to the rest of the positions. You can turn the sentence, "A dog is chasing a person," into a matrix consisting of vectors, which represents keywords.
That sounds intuitive and easy to implement.
True. But what do you think about efficiency?
Good call. It might not be that efficient. I can imagine a gigantic matrix with 99.99% of elements being 0. This sparse matrix can lead to computational waste and model overfitting.
Yes, low efficiency is one big con. Any other disadvantages you can think of?
What about semantic meanings? This simple representation of yes or no as 0 and 1 in the vocabulary doesn't reveal any relationships between words and sentences. For example, a dog is chasing a person and a person is chasing a dog would have the same representation with the basic vectorization technique despite their opposite meanings.
Brilliant.
Thanks. I learned it from the Natural Language Processing on Google Cloud course. It has an in-depth explanation about the text representation techniques and various NLP models and algorithms. Feel free to scan the QR code here or check the link in the reading list.
Perfect. Thank you, Tate.
So, how can you solve these problems?
Let's explore a new approach called word embeddings. Let me ask you something that may seem completely out of the blue. How would you describe a dog?
What? Well, a big fluffy German Shepherd? He looks exactly like my puppy, who loves to play fetch.
Exactly. You actually describe the dog with multiple dimensions: their breed, size, coat color, relationship to you, and their behaviors. How about a word? How do you describe, say, Paris?
Oh, I get what you mean. Similarly, I can describe a word based on different properties like its nature, capital city, location, Europe, origin, and even the memories and emotions I associate with it.
Imagine you create such a multidimensional space. Each dimension represents a property of words. You can project the word to this space with quantitative values. You then get your vectors that hold semantic meanings in a vector space. Not only that, since the position of the word in this vector carries meaning, the distance between the words indicates the semantic similarities between them. Similar words are located closer together, while different words are farther apart. For example, Paris and Tokyo are close to each other, but far from apple. You can even capture the analogy between words. For example, the distance between Paris and France is similar to the distance between Tokyo and Japan. Now you have Paris minus France plus Tokyo equals Japan.
Wow, that's amazing. Now I can play with words in the same way I play with numbers.
Exactly. Word embedding, or text embedding in a broader sense, is a technique to encode text into meaningful vectors. Compared to basic vectorization techniques like one-hot encoding, text embedding converts text into low-dimensional, dense vectors that retain semantic meaning.
Now I understand the idea of embeddings, but how can I develop such an encoding system to turn text to vectors?
Instead of manually specifying the values for the embedding, you train a neural network to learn those numbers. You can extend the same approach to convert multimodal data, such as images, audio, or video, to embeddings. These are called multimodal embedding. These embeddings share the same embedding space. This way, you can find that the text dog and the image of a dog are located near each other.
That sounds fantastic. But do I have to train such neural networks myself? As training on a large corpus typically requires a great deal of computational resources.
The good news is no. Instead, you can use pre-trained embedding models through APIs. For example, you call models like text embedding and multimodal embedding on Google Cloud. These models translate multimodal data into embeddings for you.
Perfect. How can you create embeddings with BigQuery then?
It's as simple as 3 steps. Note, with BigQuery, you can either use SQL queries or a Python notebook. The code is similar between the two, so choose whichever coding tool you're more comfortable with. You first need to connect the remote embedding models like text embedding on Vertex AI, assuming you've already created the resource connections and granted the necessary IAM permissions. You then upload the data. For example, you can import text data from Google Cloud Storage if you haven't already uploaded it to BigQuery. Third, generate embeddings by using a function called ml.generate_embedding. This function sends a request to the embedding model and receives embedded vectors within BigQuery queries. You can find more coding examples in the following demo and the hands-on lab. You save the results to a table. You can then use these embeddings for various tasks. For example, semantic search, similarity analysis, and recommendations.
Fantastic. Thanks, Professor Diane. I learned a lot.
Up for a challenge?
Sure.
What does multimodal embedding do? A, it creates a vector space. B, it uses one-hot encoding to code text into numbers. C, it identifies the sentiment expressed in a picture. D, it converts multimodal data to a numeric representation while retaining its meaning.
Definitely D. The rest are either incorrect or partially correct.
Awesome. Let's move forward to the next step along the RAG pipeline, vector search, in the next lesson.